Good morning, everybody. Hi to all. I am Vempati Srinivasulu, Assistant Professor of Chemistry, Nagarjuna Government College, Nalgonda. Today, we will discuss Carbanions 1, Part 2. In the previous lesson, we have discussed about carbanions. What are carbanions? Types of carbanions, how they generate, stability of carbanions. All these things are discussed in the previous class. Before going to today's class, once we recap the previous class. What are carbanions? A carbon with negative charge, a trivalent carbon with negative charge called carbanion. Carbanion is a reaction intermediate in organic reactions. There are so many reactive intermediates like carbocation, carbanion, nitrene, carbene, free radical, etc. Among those, one of the reactive intermediate is carbanion. This carbanion is generated through carbon hydrogen bond heterolytic cleavage. Due to heterolytic cleavage, carbanion is generated generally. This carbanion generally it exhibits sp3 hybridization. Whenever carbon with a trivalent 3 sigma bonds with a low electron, it shows sp3. But there are some cases it also exhibits sp2 and sp depending upon the pi bonds attached to the carbon. This carbanion, trivalent carbanion, exhibits pyramidal shape like ammonia molecule. These carbanions are different types: methyl carbanion, primary carbanion, secondary carbanion, tertiary carbanion. Methyl, ethyl carbanion, isopropyl carbanion, tertiary butyl carbanion. So how these are generated? These are generated in various reactions like removal of proton from organic compound or decarboxylation of carboxylate ion or addition of a nucleophile like cyanide ion or bromide ion to the carbon-carbon double bond, or in the formation of organometallic compounds we will observe carbanion generation. These are the different reactions in which carbanions generated. Coming to the stability, whenever carbanion, we will discuss about stability. Carbon which is attached to the electron withdrawing group or electron releasing group. Electron withdrawing group, electron attracts from the carbanion, thereby those groups shares this minus charge. That's why it is stabilized. In contrary, whenever electron releasing groups are present to the carbanion, it is destabilized by its electron releasing effects. So in general, inductive effect, mesomeric effect, delocalization of electrons are the three different factors which affect the stability of carbanion. So we'll discuss different carbanions, the stability, and compared with the different examples. This is the recap of the last class. Today we'll discuss acidic nature of hydrogens. Hydrogens attach to the alpha carbon atom with respect to the electron withdrawing groups such as carbonyl, nitro group, carboxyl group and cyanide group. So these are the different groups. You see, nitro group, carbonyl group, cyanide group. Whenever these groups are attached to a carbon, if that carbon bears an hydrogen, that is called alpha hydrogen. Okay, so these hydrogens are acidic in nature. How? These hydrogens are easily removed as protons. Carbon-hydrogen bond is weakened by attraction of electrons towards electron withdrawing group. That's why there is a generation of carbanion taking place. It loses its proton. So generally these groups are called active methylene groups. Whenever a carbon CH2 group is linked to electron withdrawing groups like carboxyl or ester or cyanide or nitro, those are called active methylene groups. These active methylene containing compounds generally show acidic nature due to presence of alpha hydrogens. Generally, these formed carbanions are stabilized by minus inductive or negative mesomeric effect groups. Acidic nature of a compound is measured in terms of Ka values and pKa values. The more the Ka value, more acidic in nature. Acidity is inverse proportional to pKa values. Logarithm of Ka value is called pKa. Generally, we'll express pKa values of different acids. So acidity is directly proportional to the stability of carbanion. If there is a compound which lost a proton by forming a carbanion, if it is stable, we can say that hydrogen is more acidic in nature. So anyhow, acidity will measure the acidity of different organic compounds in terms of pKa values. Lesser the pKa value, more acidity of particular hydrogen. You see in this, okay, so this is a carbonyl compound. In presence of base, it abstracted its base, it's abstracted a proton from this compound, forming a carbanion. This is a carbanion. This is stabilized by a resonance. So these are the resonance structure of this carbanion. Inlet ion and carbanion both are resonating structures. That means this minus charge is delocalized from carbon to oxygen. This is a resonance hybrid. So that means this minus charge is delocalized from carbon to oxygen. So minus charge is shared this negative charge. These three atoms share this minus charge. That's why it is stable. That's why the hydrogen is acidic, you can say. In the second example, this is diethyl malonate. In this diethyl malonate also, this carbon having two hydrogens. These hydrogens are easily removed as protons in presence of base. That's why it is also carbanion. So this is also acidic in nature. Coming to the next point, next slide. Third example, nitroalkanes. nitroalkanes, whenever this hydrogen is lost to the base or any ethoxide or hydroxide or alkoxides, it forms its corresponding carbon ion. So that's why alpha hydrogens which are attached to the nitro group, so nitro containing groups, also show acidic nature. Methyl cyanide. Methyl cyanide, a compound, its conjugate base is a methyl cyanide carbon ion. Its pKa value is 25. Whereas ethyl acetate compound, its carbon ion has pKa value 25. Then these are the different pKa values for different organic compounds. And there is third one is acetone. Acetone carbon ion is a conjugate base. It has 20 pKa value. Then acetaldehyde, its pKa value is 17. So hydrogen, whenever it lost a hydrogen, it forms its corresponding carbon ion, which is also called conjugate base. Diethyl malonate, its conjugate base, it shows 13 pKa value. These are the different pKa values for different organic compounds which has active hydrogens, acidic hydrogens. Okay, we'll see some more compounds. You see, acetyl, 1, 2, 3, 4. Ethyl butanoate, 2-oxo ethyl butanoate. It's also called ethyl acetyl acetate. Ethyl acetate, EAA. It also forms its conjugate base by losing one proton. Its pKa value is 11. You see, very less. That's why it is more acidic. These hydrogens are more acidic. Whereas acetyl acetone, it forms its corresponding conjugate base, carbon ion. It shows 9 pK value. So 9 value is very less compared to others. That's why it is more acidic. These hydrogens are more acidic. Coming to the ethyl alcohol, pK value is 15.9. So when we compare these compounds with our active methyl compounds. Okay. So acetic acid pK value is very less. So pK value less means stronger acid. Okay, this is a these are the different pK different pK values for different compounds. So pK value, by observing pK value, you can say whether it is a strong acid or not, whether hydrogen, the particular hydrogen is acidic in nature or not. If the pK value is more, we can say that is stronger acid. This is about acidic nature of different hydrogens. Okay, coming to the next topic in this chapter is tautomerism. Tautomerism. What is tautomerism? So, how it is exhibited? What are tautomers? What is tautomerism? What is tautomerization? What are the necessary conditions to a compound to exhibit tautomerism? So all these things we will learn one by one. Okay. Today, okay, we'll continue the class tautomerism. Tautomerism. So what is tautomerism? Okay. What is tautomerism? How a compound exhibits tautomerism? What are the required conditions for tautomerism? What is tautomerization? What are the different compounds which exhibits tautomerism? We'll discuss these things. When two structural isomers are mutually interconvertible and exist in dynamic equilibrium, they are called tautomers. That phenomenon is called tautomerism. So once again, these are structural isomers. That means constitutional isomers. There is a change in functional group. So when two structural isomers are mutually interconvertible and exist in dynamic equilibrium, that means one isomer converts into other isomer rapidly, then that phenomenon is called tautomerism. The formed isomers are called tautomers. So tautomerism is a dynamic phenomena. So tautomerization means conversion of one tautomer into other tautomer is called tautomerization. So in this tautomerization, what is happening? Change in functional group is taking place. So let us take one example. So this is a compound. What is the necessary condition to exhibit a compound? To exhibit tautomerism is a compound should have alpha hydrogen, and a compound must have a double bond. You see, this is a double bond. X double bond Y. For example, carbonyl, in carbonyl C double bond O, in nitro N double bond O and NO, nitroso NO, imines CH double bond N, NH. So like that, there should be a double bond group. So minimum condition to exhibit tautomerism is it should have an alpha hydrogen. At the same time, it should have a double bonded group. Double bonded group, there should be a alpha hydrogen to the double bonded group. There is a necessary condition, a compound to exhibit tautomerism. So what is happening here? You see, okay. So this hydrogen bond is this bond electron moving towards here. At the same time, this bond is polarized to here due to difference in electronegativity. So what is happening? You see, this H is shifting. This H is shifting from here to here. This H is shifting from here to here. At the same time, double bond is shifting from here to here. You see, H is shifted to Y. This bond is shifted to C double bond X. So double bond and H is shifting mutual opposite to each other in this tautomerization. So H is shifting towards Y and double bond is shifting from here to here. So that's why in this case double bond and proton is mutually changing its positions in opposite directions. It is moving. Then there is a these two are called tautomers. Which one? These two are called tautomers. So proton shifted from one carbon to other group, So due to shift of proton and double bond, tautomerization takes place. Okay, this is tautomerism. Tautomerism is a structural isomerism. Why? Because there is a change in functional group. It is also called constitutional isomerism. A double bonded group which has an alpha hydrogen attached to the carbon generally show tautomerism. The two isomers are called tautomers. Conversion of one tautomer into another tautomer is called tautomerization. So, change in function group is taking place in this phenomena. Okay, next slide. Okay, you see different examples. In carbonyl compounds, what is happening here? This is a carbonyl compound. You see, isn't it? It's a carbonyl compound. This is a carbonyl group. To this carbonyl group, this is alpha carbon. This is alpha carbon. This carbon. This carbon has one hydrogen. It is called alpha hydrogen. This shift of hydrogen is taking place from here to here. You see, this hydrogen is shifted to oxygen. At the same time, this bond is shifted from here. If this bond is shifted to here. So here. So that's why in carbonyl compounds it is called keto-enol tautomerism. So it is called keto form. It is called keto form. It is enol form. So there is equilibrium between these two. That's why it is called keto-enol tautomerism. We'll see in nitro compounds. Nitro compounds also exhibit this type of tautomerism. You see, not all compounds, nitro compounds which possesses alpha hydrogens. This is a nitro group, this is alpha carbon, this is alpha hydrogen. So alpha hydrogen containing nitro compounds also exist in two forms. One is nitro form, this is a nitro form, this is acid form. Why? Because the OH is acidic in nature. Double bond, the OH group is attached to double bond. That's why it's called enol form. It is also called acid form in nitro compounds. Coming to the next example, imines. So CH double bond N is called imine group. This is imine group. You see, this is imine group. So imines which contain alpha hydrogen also exhibit tautomerism. It is imine, it is enamine. Why enamine? NH group is amine group, double bond is ene. So both are in the same compound. That's why it is called enamine. So imines is converting into enamines by change of position of proton from carbon to nitrogen. So also this is a second example. See the third example, nitroso compounds. So nitroso compounds also exhibit tautomerism. You see, this is a nitro compound. This is nitroso compound. NO group is there. There is a alpha hydrogen. This bond electrons shifted to here. At the same time, this pi bond is polarized to here's oxygen. So the hydrogen is shifted to here. So hydrogen shifting to here. Hydrogen shifting to oxygen. Double bond shifting to carbon nitrogen bond. That's why the double bond and OH. This group is called oxime. This is oxime. Okay. So nitroso compounds is in equilibrium with oxime. These two also called tautomers. Why these tautomers? There is a proton shift from carbon to higher electronegative atom which is adjacent to the carbon. Okay. So what are the minimum conditions to exhibit tautomerism is a alpha hydrogen. There should be a alpha hydrogen and a double bonded group should also be present. So there should be a alpha hydrogen which is linked to the carbon in this compound. This is about tautomerism. So in general, carbonyl compounds, nitro compounds, nitroso compounds, imines exhibits this tautomerism. Okay, right. Okay, 1, 2, 3. Okay, we'll explain a tautomerism in different classes of compounds. And in our syllabus, we have to discuss this tautomerism in carbonyl compounds and nitro compounds and ethyl acetate and diethyl malonate. We will take one by one and we'll discuss detail. So in tautomerism is exhibited in carbonyl compounds, just now we have discussed. So how? So this is a carbonyl compound. Once again, this is a carbonyl compound. This is a alpha hydrogen. This alpha hydrogen, why it is attracting towards oxygen, that's we have to discuss. So this carbonyl group is electronegative group. This attracts this carbon electrons towards this. So then this carbon becomes electropositive. This carbon becomes electropositive. That's why this CH bond will be weakened. So that's why this CH bond is undergo heterolysis, unequal fission, cleavage of the bond takes place. This proton shifts to here oxygen. So that's why there is a double bond formation between carbon and OH bond formation between O and H. So this is enol. We call this is a keto form. This is enol form. What is enol? Double bond we call enol alcohol. So in the same compound we have double bond and alcohol. That's why we call as enols. The two, this hydroxy group is attached to double bond only. That's why it is called enol. So carbonyl compounds exhibits keto-enol tautomerism. So what is the necessary condition? Just now I told you, to exhibit tautomerism there should be an alpha hydrogen and a double bonded group. That should be. So in carbonyl compounds, those carbonyl compounds which have alpha hydrogens only exhibit keto-enol tautomerism. We see, we will take one by one whether a compound exhibits this tautomerism or not. So you see this one, acetaldehyde. It has 3 hydrogens. That's why it exhibits keto-enol tautomerism. Second example, acetone. Acetone has 6 hydrogens. With 3 hydrogens, 3 hydrogens. That's why this also exhibits keto-enol tautomerism. In the next class, formaldehyde. Formaldehyde has only one carbon. There is no other alpha carbon. That's why there are no alpha hydrogens. That's why this doesn't exhibit keto-enol tautomerism. So coming to the next, this one. What is this? 1, 2, 3. Propanaldehyde. 2,2-dimethyl propanol or propanaldehyde. So in this carbonyl compound is also carbonyl compound. It has alpha carbon, but this alpha carbon is attached to 3 methyl groups. That's why there are no alpha hydrogens. This compound doesn't contain alpha hydrogens. That's why this compound doesn't exhibit keto-enol tautomerism. Then coming to the cyclohexanone. This cyclohexanone has 4 alpha hydrogens. That's why this compound exhibits tautomerism. Coming to this compound, you see, this is also cyclohexanone, but it has 4 methyl groups attached to the 2 alpha carbons. So in this case, these 2 carbons are alpha carbons. Why? It is linked to the carbonyl carbon. But there are no hydrogens. This is a methyl group, this is methyl group. So 4 methyl groups are there. So thereby there are no alpha hydrogens. That's why this compound also doesn't exhibit keto-enol tautomerism. Coming to the benzaldehyde. This is also carbonyl compound. Aldehyde group is there, but in this case also there is no hydrogen in this carbon. This is alpha hydrogen, is it? This is alpha hydrogen. This is alpha hydrogen, but this carbon, this is alpha carbon, but there is no alpha hydrogen. There is no hydrogen in alpha carbon. That's why it does also doesn't exhibit keto-enol tautomerism. Coming to acyl stone. So this is this is a cell group. It is a stone. Or 1 2 3 4 2 4 dione 1 2 3 4 5 pentanone. So penta 2 4 dione. It's also called acetyl stone. In acetyl stone, we see there is a active methylene group. This is the active methylene group. Why? Because this methylene group is attached to two carbonyl carbons. That's why the hydrogen link to this carbon is more acidic in nature when compared to the other. That's why it also exhibits tautomerism. So these are the different examples which shows tautomerism. So in general, a carbonyl compound to exhibit tautomerism, it should have alpha hydrogens. Okay. Next. So keto forms, when you see the percentage of concentration of different keto and enol proportions, you see when you compare these keto enol, generally keto forms are more stable than enol forms. Enol forms are, where in certain cases enol forms also stable, we can isolate, we can separate. So in this acetone, 99%, 99.9% acetone ketone form, and only 0.1% is enol form. Why? Because this is unstable. This is stable. Coming to the next example, you see this type of compound. It has a ketone, isn't it? It's a ketone. It is enlarges to this is enol. It's a phenol. So this is a 99.9%. It's 1%, 0.1%. Why? This is stabilized. This is benzene ring. This is benzene ring. We know aromatic compounds are more stable. That's why this is phenol is more stable than cyclohexanone. Okay, this is a 1 2 3 4 2 4 diene. So this compound is very unstable. Even though it's a keto group, it is unstable. It exists only 0.1%. This one is existing 99.9%. That means it's stable. So in all cases, enols are not in minor proportions, lesser proportions. It depends upon the stability the structure of the compound. Coming to the acetyl stone just discussed. In acetyl stone, keto form is only 24%, whereas enol form is 76%. Why this is? Due to this enol is forming a 6-membered ring. You see, 1, 2, 3, 4, 5, 6. 6-membered ring is there. This there is a hydrogen bond between. There is a hydrogen bond between. Okay. There is a hydrogen bond between H and oxygen. This dotted bond is called hydrogen bond. So due to hydrogen bonding and 6-membered ring formation, it is more stable. That's why this enol is in 76% when we compare to keto form. So generally keto forms are more in proportion, but there are some instances enol forms also dominates. So depending upon the stability of the compound. Okay. Then keto enol, what is the tautomerization? How one tautomer is connected to other tautomer? What is the mechanism? So in carbonyl compounds, it is stabilized by both acid and base. First, we'll discuss acid catalyzed mechanism. This is carbonyl compound which containing an alpha hydrogen. So this is alpha hydrogen. It is a carbonyl group. So what happens? First, in presence of acid, this group undergo protonation. So you see this proton is attached to this oxygen. Due to protonation, it forms a protonated compound. Then followed by abstraction of proton towards base. This base abstracts a proton alpha hydrogen. This alpha is lost to the boron base. It is, that's why this carbon-hydrogen bond shifts here. This bond polation takes place. Why? Because oxygen plus charge is unstable. Oxonium are unstable. To get stable, it attracts pi bond electrons towards that. At the same time, hydrogen carbon bond shifts to the carbonyl and carbon. That's why enol form, keto form changes to enol form. Okay, this is a keto form, this is enol form. You see? So this is a keto form, this is enol form. So keto form is converted into enol form through this type of intermediate. So this is the mechanism in acid catalyzed condition. Okay, coming to the base catalyzed. So base, what is base? Base means an electron donor which has electron pair and negative charge. So this is base. Base abstracts this alpha hydrogen. Okay, this base abstracts alpha hydrogen. What happens? This bond shift here and this pi bond polarizes to here. Delocalization takes place. So what happens? It is a formation of an enolate ion. So this is enolate ion. This enolate ion abstracts a proton from acid. It forms enol. So in this way, keto groups are converting into enol. This is a keto group. This is enol group. So conversion of interconversion of from keto to enol is taking place through formation of an enolate ion. In many compounds, this enolate ion is more stable. It is isolated. It is separated. So this enolate is very important in organic reactions. Due to using this enolate ion, there are so many synthetic conversions are there in organic chemistry. Okay, this is a acid and base catalyzed mechanism of carbonyl compounds tautomerism. Okay, then tautomerism in nitro compounds. In nitrohydrocarbons, we discuss about something about this. So nitrocarbons also exhibit similar to keto tautomerism, similar to keto in tautomerism. Which compounds have alpha hydrogens? So nitrohydrocarbons which has alpha hydrogen only exhibits this type of tautomerism. You see, so these are the alpha hydrogens. This is the NO group is there. So two required essential conditions: alpha hydrogen should be present and nitro one double bond group also should be present in that molecule to exhibit tautomerism. So what happens? This hydrogen shifts from here to here. This hydrogen shifts here to here. Double bond shifts here to here. That's why these two are tautomers. This one, two are what? This one and this one. This one and this one, two are tautomers. It is similar to keto form, not exactly keto form. It is called nitro form. Okay, this is a nitro form. This is SE form. Enol. This OH, this H group, it is replaced by bases, metal ions. That's why it shows some acidic nature. Just now we discussed. It has some pK value. That's why it is called acid form. Simply SE form. Okay, that means primary and secondary nitrocarbons only. Primary and secondary nitrohydrocarbons only exhibit tautomerism. Why? These only possesses prime alpha hydrogens, whereas tertiary nitrohydrocarbons doesn't exhibit tautomerism. This type of tautomerism. So we'll see in the next slide. Okay, you see. Nitromethane, nitroethane. These two are nitromethane, nitroethane. This is nitromethane. This is a nitroethane. So these two are primary nitrohydrocarbons. These two has alpha hydrogens. It has 3 hydrogens. It has 2 hydrogens. That's why it exhibits tautomers. This is a nitro form. This is a nitro form, this is a acid form. Is a nitro form, it's a acid form. So proton is shifting from carbon alpha carbon to nitrogen oxygen bond. So in the second case, in the other case is a secondary nitrohydrocarbon. Secondary. Why? Because secondary, this carbon linked to two alkyl groups. So it has one alpha hydrogen. That's why this also shows tautomerism. In the case of tertiary, it doesn't exhibit tautomerism. So primary, secondary, and tertiary. When we compare these, when we observe these, only primary and secondary nitrohydrocarbons only exhibits tautomerism. Tertiary nitrohydrocarbons doesn't exhibit tautomerism. Okay. Okay. Tautomerism in ethyl acetate. This is the structure of ethyl acetate. This is ethyl acetate. This ethyl group. The acetyl group is there. Ethyl acetoacetate. So it also can be written like this also. This is also ethyl acetoacetate. So there is an active methylene group. This carbon is having active methylene group. So it also exhibits tautomerism. So shifting of proton from methylene group to carbon oxy double bond. So in this case, it is a keto form. It's a keto form. It is enol form. You see, enol form is 10%, keto form is 90%. Okay. What is happening here? You see, this H is shifting carbon hydrogen bond, a bond electron shifting to carbon, this bond. At the same time, this double bond is shifting polarization to oxygen due to higher probability of oxygen. That's why enol formation taking place. So that's it. So ethyl acetate also exists in two forms, keto form and enol form. In between, there is a dynamic equilibrium. Keto form exists in 90% and enol is 10%. Facts favor of keto form. So how will say the compound exists two forms? We know carbonyl compounds react with sodium bisulfate, giving bisulfate adduct. And the carbonyl compounds undergo addition reaction with HCN, and it forms cyanohydrins. You see, sodium bisulfate adduct with cyanohydrin with HCN, oxime with NH2OH, hydrozones with phenyl So all these reactions are exhibited by our ethyl acetate. So which shows a carbonyl group is there. That means keto form is present. Coming to the enol form evidences. So enols are easily react with sodium metal. Enols easily alcohol groups easily forms acetyl derivatives with acetyl chloride, and phenolic OH group gives violet color with ferric chloride. So all these reactions are exhibited by ethyl acetate. That means ethyl acetate, it has two forms. One is ketonic form, one is enolic form. For above four properties due to carbonyl group, below three properties due to enolic group, L1OH group. That's why we can confirm that ethyl acetate exists in two forms. One is keto form and there is enol form. These are the evidences. Next slide. In the similar way, diethyl malonate. See, this is a malonic acid. If there is a if so This is a malonic acid. If there is a COH, we can say this is a malonic acid. But ester, so diethyl ester of malonic acid. That's why we call diethyl malonate. Okay, this diethyl malonate also has a active methylene group. This methylene group is called active methylene group. Why? It is flanked by two electron withdrawing groups. That's why hydrogen attached to this carbon is more acidic in nature. That's why this compound also exhibits tautomerism. You see, this proton is shifted from carbon to oxygen. You see, this proton is shifted to from carbon to oxygen. It forms enol. So there is equilibrium between keto and enol. This is a keto form. This is the enol form. This is also established our previous properties. This compound also exists in two forms. That's why how can we say this compound? If this compound reacts with HCN, giving cyanohydrin, this compound gives sodium bisulfite attack. This compound gives phenylhydrazone. So these are the evidences for containing carbonyl group. In other case, in other words, in enolic form, enol form gives a ferrichloride test, and what we discussed in the previous slide. So the this compound shows enol group. It contains enol group as well as keto group. That's why we can say this compound exists in two forms. So this is a tautomerism in diethyl malonate. So this is about our this chapter. Today's class, what we have discussed in this class: what are acidic alpha hydrogens, which compounds contain acidic alpha hydrogens, then what is tautomerism, which compound, what are the primary conditions of a molecule to exhibit tautomerism. Then we studied different tautomers in different classes of compounds: carbonyl compounds, nitro compounds, and ethyl acetate, diethyl malonate. These two are active methylene containing compounds. So we have discussed tautomerism in these four types of compounds. Thank you very much. We'll see you in the next class. Thank you.